Okay, ELE 115L. We're on lab 6, which has a parallel RL circuit. And I'm just going to do the computational background so that you can compare with what you measure. We have 8 volts peak to peak at 5 kilohertz for our source. Driving 330 ohms in parallel with 10 millihenries. Remembering, in parallel circuits we have one voltage. This total voltage here is equal to the voltage across the resistor, right? And it's also equal to the voltage across the inductor. So there's just one voltage there. There'll be multiple currents. There's a total current, and that total current splits, and you have a current through R1 and a current through L1. So one of the things I'm going to suggest here, just to kind of be more like the Sen gauge materials, I'm going to use RMS. So we have peak to peak, so we've got to divide that by 2 to get to 4 volts peak, and then divide it by the square root of 2 to get to 2.828 volts RMS. All right. So now we have IR1 is equal to VT over R, because the voltage across R1 is this total voltage. So 2.828 volts RMS. Maybe I can make this whole thing a little bigger here. This is preview. Here we go. So the current through R1, the voltage across it is V total, and the resistance, of course, is R. It's Ohm's law. So we have 2.828 volts RMS at 0 degrees, because our sources are always at 0 degrees, divided by 330 ohms at 0 degrees. Resistors are 0 degrees. And we come up with 8.57 milliamps RMS, again keeping it all the way through, at an angle of 0, because 0 minus 0 is 0. Now our real power is only the power dissipated in the resistor. If this is a pure inductor, which it supposedly is here, then no power will be dissipated in the inductor. So P real is equal to V R1 times IR1, and as we've already said, VR1 is essentially V total. We used it up here, right? So VR1 is essentially not essentially, it is V total. So V total times IR1 equals 2.828 volts RMS at 0 times 8.57 milliamps RMS at 0. And so a couple of voltage times the current, both at 0, is just going to give us straight watts, although this is milliamps. So we wind up with 24.24 milliwatts of real power. So let's find our inductive reactance. And XL1 equals 2 pi FL. This should really say L1, shouldn't it? But at any rate, so here's 2 pi, 6.283. Would have to be close enough for us. Times 5 times 10 to the third. That's 5,000 hertz, 5 kilohertz. 5 times 10 to the third hertz times 10 times 10 to the minus third henries. This is 10 millihenries. 10 to the minus third is milli. So we multiply all that together. The 10 to the 3 plus a negative 3 is 10 to the 0, which is 1, so that term drops out. 6 times 5 is about 30, so 6.283 times 5 is 31.42, and then we have to multiply by 10, so we get approximately 314 ohms, and we know that that is at 90 degrees. I should have put it there, but you know, inductive reactance is always at positive 90 degrees. So let's look at the current through this inductor. Once again, you know, this could be VL1, but we know that VL1 is the same as VR is the same as VT. So VT over XL1 is 2.828 volts RMS at 0 divided by 314 ohms at plus 90. And this winds up giving us about 0.009 amps RMS at 0 minus 90, or 9 milliamps RMS at minus 90 degrees. And that's going to wind up going right there where the red arrow is. Now, the reactive power, just like we could compute the real power using the resistor only, we can compute the reactive power. Sorry about that. Okay. We can compute the reactive power by considering just what the inductor only. So we can take, I could take IL1 times VL1, or I could take I squared L times XL, and in that I would get 9 milliamps. And again, with reactive power, we don't need phase angle because it's all reactive. You know, the 9 milliamps points down at 90 degrees, and this 314 points up at 90 degrees, so it would come out at 0. Well, it might come out at 0 degrees, but in fact, it's a reactive quantity. So volts amperes reactive is equal to that, and I get 25.4 millivolt amperes reactive. If I multiplied IL1 by VL, I would get 9 milliamps times 2.828 volts. And let's see, how would that work out? So I'd get, it's almost 3 times 9 would be 27, so 25.4 is seems valid. So we could have calculated that two ways. We could have taken, VL1, which is the same as V total in this parallel circuit, times IL1. I did the I squared R equivalent here, but either case you can see that something close to 3 times 9 milliamperes would get you up close to 27 millivolt amperes reactive. Yes, and we got 25.4, so I think we're in the right ballpark there. If we want the total current, there's a couple ways we can get it. We can add these two currents, and the resistive current IR1 is going to be at 0 degrees, and the 9 milliamps, the inductive current IL1, is going to be at minus 90. So we've brought into a vector sum here, as I've indicated right there. So the magnitude of this current is going to be the Pythagorean theorem formula. I can take the sum of the squares of the other two sides, and then take the square root, and I get 12.43 milliamps RMS. And the angle, well, this angle here, theta sub I, would be, its opposite would be IL1, and its adjacent would be IR1. So we want to know what angle has a tangent of minus IL1 divided by IR1. Okay, the two currents, and it turns out to be minus 46.4 degrees. So I total, there's our magnitude for 12.43 milliamps RMS at minus 46.0 degrees. Okay, that would be that arrow right there, IT. And now we want to compute the total the total impedance, and I've got R1 and L1 in parallel, so I'm going to use the product over the sum formula, and we'll be able to check it in a minute also. But Z of t is equal to R1 times XL1, the product over the sum, R1 plus SXL plus XL1. And that, I'm calling one of these a numerator and the other a denominator. And the numerator is going to be equal to 330 ohms, R1, times XL, 314 ohms at 90. And so their product is going to be 103,602 at 90 degrees. The denominator is a vector sum, okay, where I have to add these two and get, I put ZT there, not actually ZT, is it? It's this guy right here is really this D, or denominator term. So, sorry about that. So at any rate, D is a vector sum. It's going to be equal to 330 squared plus 314 squared, the square root of that sum. So I get a denominator of, the magnitude of the denominator will be 455.5 ohms, and the angle of the denominator is the vector sum. It'll be the angle whose opposite, which is 314, over adjacent, which is 330. The angle whose tangent is that, and we come up with a 43.6 degrees. So on top we have 103,602 at 90, that's N right here. In the denominator we have 455.5 at 43.6. When you divide these two, you get 227.5 ohms. Subtract the angles, 90 minus 43.6, we get a 46.4 degree angle. Okay, and now if we wanted to check this, we have the total current up here, and the total current was 12.43 milliamps RMS at minus 46. So if I develop, I'm going to take my calculator here. I should put this in here. We could have found ZT just by dividing VT by IT, all right? And so if I do this, I have that VT equals 2.828 volts RMS, and of course that's at 0 degrees, and I'm going to divide by 12.43. Now for milliamps I can put times 10 to the negative 3 here, and I get 227.5 is the magnitude, so that's good. And 0 degrees minus a minus 46.4 is going to be like 0 degrees plus 46.4, and so we're going to get this very same number here. I did the total impedance the long way. You can also, if you know V total and I total in vector form, you could divide those and get the same number. Okay. Now, our apparent power is equal to the magnitude of the total voltage times the magnitude of the total current, and that's 2.828 volts RMS times 12.43 milliamps RMS, and we get 35.15 millivolt amperes. And if we do the check on the Pythagorean thing, remember volt amperes, apparent power is the hypotenuse, and real power and reactive power are the other two sides. So if we square the real power and the reactive power, it will be equal to this number right here. This number squared. And that does check out, and you can do that yourself, but I did it and declared victory and just wrote yes. Power factor, there's a number of ways to calculate it. You can take the magnitude of the resistor current divided by the magnitude of the overall current. You take 8.57 milliamps RMS divided by 12.43 milliamps RMS, and you get approximately 0.69. Some people like to express power factor as a percentage. You multiply this by 100, you get 69%. Now, this formula here is only for parallel circuits, just as in the series circuit, it was R over ZT, not ZT over R. But for a parallel circuit, we got our 227.5 ohms, divided by 330 ohms. It again comes out to 0.69, multiplied by 100, you get 69%. Another way to get power factor is to take the ratio of the real power divided by the apparent power. That would be 24.24 divided by 35.15. You get 0.69 multiplied by 100, you get 69%. And the last is to take the power factor, take the angle of the current, the cosine of the angle of the current, and the cosine of minus 46.4 degrees is, once again, 0.69 multiplied by 100, got 69%. So it all worked out very nicely there. And before I post this, I may put in the other computation for Z sub t here, the total impedance. This is the hard way. I'll put the easy way in there as well. Okay, I don't remember any other mistakes here. Maybe I should put L1 right there or something, and I think that ought to cover it. So we'll see you in lab. In lab, you'll have, I don't think you'll have to do this kind of computation in lab, but I wanted you to be able to see that you could, after seeing an example done, you could compute everything you would want to know about that lab circuit. So, okay, we'll see you next time. I'm not going to do this, the second circuit in the lab, because it's, the same circuit with some different values, and there's no need to go over that. So, once again, take it easy, and we'll see you soon.